Earlier, we looked briefly at what is called a difference amplifier, and specifically we looked at a balanced difference amplifier, which takes the difference in two input voltages and amplifies it. In the balanced difference amplifier, the two input resistors are the same, we'll call it R, and the other two resistors have some value A times R, where A is the desired gain that you want to multiply the difference in the two inputs by. Now here we're simply going to use a gain of 1, which means all four resistors are the same. When we first covered this, we glossed over it and did not talk much about it at all, but there are several problems with the basic difference amplifier. One has to do with what is called the common mode rejection ratio. Now, since you're looking at the difference in two signals, those two signals may have some common value added to them. For example, it's not uncommon for both of them to have a small 60 hertz signal that has just been picked up electromagnetically from the environment, because there's 60 hertz all over the place. So that's fairly common, but there are many other types of common mode signals. Now ideally, since the signal of interest is just added to that common mode signal, since it's a difference amplifier, ideally the contribution of that common mode would be 0, so it would not affect the output. Now, as is usually the case, things aren't perfect, and so you actually do get some of that common mode signal feeding through to the output. Now, there are things we can do to dramatically reduce that common mode output and increase what is called the common mode rejection ratio. Ideally, common mode rejection ratio is going to be infinite, but you certainly want it to be very high. We'll talk a lot more about common mode rejection ratio when we talk about some more non-ideal characteristics in Chapter 4. But for the moment, that will suffice. If you had an ideal op-amp, which of course you don't, and if the two pairs of resistors were perfectly matched, which they're not going to be, then your common mode rejection ratio would be really high, hopefully infinite. But let's for the moment assume that the op-amp is ideal, so it has an infinite common mode rejection ratio just on its own. The problem here is that the resistors are not going to be perfectly matched. Now, typically what you do is, in order to account for the differences in the resistors, you make one of those resistors variable, and typically the one that you choose is the one from the non-inverting input to ground. To begin with, you're probably going to pick 1% resistors for those four resistors, so they will be fairly closely matched. But when you choose them, and we'll just use this example with a gain of 1 so all the resistors are the same, what you'll do is you'll pick a value for R, and then for that one resistor you're going to make variable, you will select the nearest 1% value below that chosen R for that resistor, but you will put a small trimmer potentiometer in series with it, and the value of that trimmer potentiometer would be about twice the difference between R and that next nearest value below R. For example, if you chose R to be 100K, which is of course a 1% value, the nearest 1% value below that is 97.6K. Now that's 2.4K below 100K, and twice that value is 4.8K. Now, you're not going to buy a trimmer potentiometer with a value of 4.8K. So what you do is you choose a standard value, and certainly 5K is a standard potentiometer value. So you put this 5K potentiometer in series with this 97.6K. So nominally with 97.6K in series with up to 5K, then you could adjust this about 2% to either side of 100K. And that should allow you to very precisely balance that circuit and get rid of that common mode signal. There are some other issues with common mode signals having to do with what are called ground loops, which have to do with the fact that ground paths aren't perfect. They actually have some resistance, and we will talk about that in another video very soon.